I want you to just picture something for a second. Think about what you were doing right before you put this deep dive on.
Probably, checking a mail or something.
Yeah, exactly. Or maybe you were streaming a movie in 4K. Or maybe you were running some massive query through an AI tool for work. Or, honestly, even just pulling up a 10-year-old photo from your cloud drive.
Right.
We use that word all the time, right? The cloud.
Yeah.
We picture this, I don't know, this ethereal, invisible, weightless force floating above us, just magically beaming data into our devices.
It's a very comforting image, honestly.
It is. But if you actually stop and think about it, the reality of the cloud is, well, it's incredibly physical.
Oh, absolutely.
It is heavy. It is deafeningly loud. It is freezing cold. The cloud is actually this massively complex labyrinth of reinforced steel and, miles of fiber optic cables thick as your arm, and industrial liquid cooling systems humming in some windowless warehouse somewhere.
It's really one of the greatest magic tricks of the modern era, if you think about it. The abstraction is so seamless that we've completely lost touch with the mechanical reality that's, making our digital lives possible. It's an illusion of absolute simplicity, but it's built on top of staggering, almost incomprehensible physical complexity.
Which brings us to today. Our mission is to peel back that illusion. We've got our hands on a document that is, frankly, fascinating in its raw technical grit. We're looking at the April 2026 Getting Started User Guide for Supermicro's SuperCloud Composer.
Right, which they abbreviate as SEC.
Exactly. Specifically release 3.12.0.
I know, it sounds like an incredibly dense piece of reading.
It really does.
And to be fair, it is a highly specialized manual, but if you know how to read between the lines, this document is essentially a blueprint for the future of IT infrastructure.
A peek behind the curtain.
Exactly. It's the operator's manual for how massive scale data centers are actually tamed and managed today.
So we're going to look over the shoulder of a modern data center administrator. We're going to see exactly how this chaotic, heat-generating physical hardware is transformed into that invisible, software-defined cloud that you interact with every single day.
Should be fun.
Okay, let's unpack this. Before we get into the actual buttons and menus of this software, we really need to understand the fundamental philosophy of what it is trying to achieve.
Right, the big picture.
Yeah. The terminology here refers to SEC as a composable cloud management platform that provides a dashboard for a software-defined data center.
Okay, so those are heavy industry terms. Let's break them down a bit.
Please.
So software-defined data center, or SDDC, is the key paradigm shift here. Historically, let's say, 10 or 15 years ago, if a company wanted to deploy a new database or an application, they bought a physical metal box.
Physical server.
Right, a server. It had a CPU, it had some memory sticks, and a hard drive physically bolted inside of it. It was a fixed, static entity.
Sort of like a complete package, like buying a laptop today, just scaled up for a business.
Exactly like that. But the problem with that model is the incredible financial waste.
Oh, because of unused parts.
Precisely.
Yeah.
Imagine that server is running an application that requires a massive amount of storage, but very little processing power.
Right.
You fill up the hard drives quickly, but the CPU is only operating at, say, 5% capacity.
Right.
That 95% of unused processing power is just stranded.
It's just sitting there doing nothing.
Yeah, you can't just rip it out and hand it to another server that needs it. You've paid for resources you literally can't use.
Which is terribly inefficient.
It's awful. So what this document outlines is a complete departure from that. It relies on what the industry calls a disaggregated infrastructure model.
Disaggregated. Okay.
Yeah. If you look at how the architecture is laid out in the guide, the components of a computer system, the compute power, the storage, the network, they are physically separated into distinct pools.
Wait, so instead of buying one complete computer, I am essentially buying like a giant tank of independent parts.
Precisely. You have a massive pool of processing power over here, a massive pool of storage over there, and a high-speed network connecting everything together.
Okay.
And the SEC software acts as the brain. When an application needs to run, the software dynamically reaches into those pools, grabs exactly the right amount of compute, the exact right amount of storage, and essentially assembles a virtual computer on the fly to maximize the return on investment.
No.
It's composable. That's what the Composer in SuperCloud Composer actually does. It orchestrates these scattered parts.
Okay, so I was trying to wrap my head around this disaggregated concept earlier, and I came up with an analogy for you. Let's see if this tracks.
Oh, I love a good analogy. Go for it.
Okay, so imagine you want to build a Lego spaceship. In the old, rigid hardware days, you'd buy a specific Lego spaceship kit in a box. You build it, and it sits on your shelf as a spaceship.
Right.
Even if you only need, like, the thrusters for another project, you can't use them without breaking the whole ship apart.
Right, they're physically bound to the ship.
Exactly. But with composable infrastructure, it's like having a giant warehouse filled with millions of loose, sorted Lego bricks. You have a tablet. You tap the screen, select the thrusters you need from aisle A, the cockpit from aisle B, and the software magically, logically links those scattered pieces together over a network into a fully functional spaceship.
Yes, that's it exactly.
And when you're done playing with it, you hit a button, the spaceship dissolves back into the pool of loose bricks, ready to be used by someone else to build a castle.
That is a phenomenal way to visualize it. You are completely abstracting the physical hardware into logical software objects. The spaceship only exists as long as you need it to.
That's so cool.
It really is. And the manual actually refers to that temporary spaceship as a composed node.
Composed node. Okay. But hold on, for that software to talk to all those different loose bricks, especially if they are built by different companies, right?
Yeah, that's a big factor.
It needs a common language. The text keeps mentioning something called the Redfish Northbound API message bus.
Yes. Redfish.
I mean, I know APIs are how software programs talk to each other, but Redfish sounds like a brand of Swedish candy. What actually is that?
I can see that. But what's fascinating here is how Redfish solved one of the absolute ugliest problems in enterprise IT, which is vendor lock-in.
Oh, right.
Before Redfish, every hardware manufacturer, Dell, HP, Supermicro, Cisco, they all had their own proprietary closed-off language for managing their physical servers.
Oh, of course they did.
Right. If you bought management software from HP, it literally couldn't talk to a Dell server. It was a deliberate business strategy to force companies to buy all their hardware from one single vendor.
So if you had a mixed data center, it was just an absolute nightmare of custom plugins and translation layers and stuff.
A complete and utter nightmare. Redfish is an industry-standard RESTful API protocol designed specifically for hardware. It is an open standard that essentially forces all these different metal boxes to accept the exact same commands. When the SEC software sends a command that says, tell me your internal temperature, it sends that via Redfish.
And the hardware understands it.
Exactly, regardless of who manufactured it.
And that becomes incredibly important because the text explicitly notes that SEC monitors a, quote, wide portfolio of multi-generation servers. That really implies a hybrid approach.
Well, it's the messy reality of the corporate world, No company throws away a perfectly functional $1 million server rack just because it's 3 years old.
Yeah, that would be insane.
Right. So you have an IT environment where an administrator is trying to make a dusty 10-year-old legacy server play perfectly nice with a cutting-edge 2026 AI supercluster.
Wow.
Yeah. Redfish, combined with the composable software, bridges the gap between the old way of doing things and the new disaggregated model.
Okay, but if everything is just a floating pool of resources, doesn't that make tracking a physical hardware failure completely maddening?
What do you mean?
Well, if my logical Lego spaceship suddenly crashes, how do I know which physical brick in a warehouse of millions actually caught on fire? How does a human administrator visualize this without their brain just melting from the abstraction?
If we connect this to the bigger picture, that is exactly why the single unified dashboard, the single pane of glass, as they like to call it, is the entire selling point of the SCC platform.
Ah, okay.
The abstraction is incredibly powerful for efficiency, like we talked about, but without a map back to the physical reality, it's incredibly dangerous.
You'd be flying blind.
Exactly. The software has to be able to seamlessly translate a logical error in your compose node back to a flashing red physical light on a specific metal drawer in, say, rack 42.
Right.
And to do that safely, the software requires absolute, unquestioned control over the environment.
Which brings us to the very first thing an administrator actually has to do when they boot this software up.
Security.
Security. Before you build anything, you have to lock the doors.
Right.
We're talking about a single dashboard that controls tens of millions of dollars of hardware.
Yeah.
If a bad actor gets into this dashboard, they don't just steal data. I mean, they could physically command the hardware to overheat and melt itself down, right?
That is not an exaggeration at all. Access to the control plane is quite literally a matter of physical safety for the data center.
Wow.
That's why the very first operational procedure detailed in the manual is the Web and API HTTPS certificate replacement process.
Yeah, I was looking at this section. It provides a highly specific command line script. It's called patch.stls.esh.
Yeah.
And you feed it two parameters,
Hmm.
path to crit, which is the new TLS certificate file, and path to key, the private key file. Now, I understand the broad strokes of encryption, but the text specifically calls out a failure state.
It does.
It says the script will terminate if it doesn't find a valid PEM header. What exactly is a PE header, and why does the script care so much about it?
To understand that, we need to look at how public and private key encryption fundamentally creates trust. Think of a TLS certificate, like a highly secure, digitally watermarked passport that the data center uses to prove its identity to the administrator's web browser.
Okay, digital passport.
Right. And there are different ways to physically format that passport. A DER format, for example, is binary. It's like a hard plastic ID card, perfectly readable by machines, but complete gibberish to human eyes.
Got it.
A PE format, on the other hand, is base 64 encoded. So it looks like a block of text, and it usually starts with a highly specific header, like begin certificate, surrounded by dashes.
So the script is basically checking to make sure the passport is printed on the correct type of paper before it accepts it.
Exactly. And the reason for that strict validation is because of the underlying architecture. The script actually patches a Kubernetes deployment.
Kubernetes.
Yeah, which is a system for running containerized applications. Think of it as like shipping containers for software. It keeps everything isolated and running smoothly. The SEC web interface is running inside one of those containers. If the script were to just blindly accept a corrupted file or a file in the wrong format and inject that broken certificate into the Kubernetes web server container.
The container would crash when it tries to restart.
Worse, actually. The container would restart, but the SSL encryption would fail.
Oh, no.
Yeah, and the moment that happens, the trust bridge between the administrator's web browser and the entire data center control plane just shatters. The web interface becomes completely inaccessible.
Wait, so the entire IT team is locked out of their own multi-million-dollar data center by their own security protocol?
Yes. By strictly checking the PEM headers before applying the patch, the script actively prevents a catastrophic self-inflicted lockout.
That makes total sense. You really don't want a simple file format mistake to turn your main management console into a brick.
Exactly.
And speaking of lockouts, let's talk about how the system handles passwords. The text goes deep into account lockout policies.
Oh, this is a fascinating section.
There are 3 variables you can configure: fail count, fail window, and penalty time. I want to test the math on this with you.
Sure.
Let's say I set the fail count to 3, the fail window to 30 seconds, and the penalty time to 900 seconds.
Okay, so what that mathematical configuration does is essentially create a time lock. If anyone types the wrong password 3 times within a very tight 30-second window, the system physically jams the gears.
Right.
The account is completely inaccessible for 900 seconds, which is 15 minutes.
But wait, 15 minutes? I mean, if a hacker is using an automated botnet to try and guess passwords like a brute force attack, couldn't the bot just wait 15 minutes and try again? Is 15 minutes really enough to stop a dedicated cyber attack?
It absolutely is, because of the math of permutations.
Right.
A brute force attack relies entirely on sheer volume. An automated script wants to try, 10,000 passwords a second.
Right.
If you introduce a 15-minute penalty after every 3 guesses, it completely destroys the velocity of the attack.
Oh, I see.
Think of a bank vault with a time lock. If the dial freezes for 15 minutes every single time you try a wrong combination, it doesn't really matter how fast your fingers are. Trying a million combinations goes from taking a few hours to taking several centuries.
Wow.
It grinds the attack to an absolute halt.
Okay, that's brilliant. It's using time as a literal weapon against automation.
Exactly.
But then there's the application idle timeout feature.
Yeah.
If you don't touch the mouse for 30 minutes, it automatically logs you out. You can configure this up to 1,440 minutes, which is a full 24 hours. But a 30-minute default seems, well, incredibly annoying.
It is annoying.
Imagine you are halfway through configuring some massive server deployment. Someone taps you on the shoulder to ask a question, you grab a coffee, and when you come back, all your unsaved work is gone because the screen locked.
Yeah, it highlights the constant painful tension between security and usability in enterprise IT.
Yeah.
Yes, it's frustrating to lose unsaved work, but from a security standpoint, leaving an unlocked God-level control plane open on an unattended monitor is just an unacceptable risk.
I guess that's fair.
If a disgruntled employee or a physical intruder walks past that desk, they have complete control over the entire company's infrastructure.
Here's where it gets really interesting, though. We're talking about incredibly robust, modern security. checking PM headers for Kubernetes containers, mathematical time locks against botnets.
Right.
But then I looked at the password rules themselves. It requires one number, one uppercase, one lowercase. Standard stuff.
Very standard.
But the length, it says the password length must be between 6 and 12 characters. Wait, the maximum password length is 12 characters. In 2026,
Yeah.
I have a 16-character password on my streaming accounts. Why on earth would an enterprise cloud manager cap passwords at 12 characters?
It is a jarring detail, isn't it? In modern cybersecurity, as you just said, the trend is toward long passphrases, 24, maybe 32 characters. Capping it at 12 is almost certainly a legacy hardware constraint.
Oh, remember earlier when we talked about managing multi-generation hardware?
Yes, exactly. The dusty 10-year-old servers mixed with the new ones. Deep inside those old servers is a little chip called a baseboard management controller, or BMC.
Okay.
It's a tiny independent computer that monitors the server's physical health. SEC has to pass credentials down to those old BMCs to talk to them.
And let me guess.
Yep. Some of those legacy hardware chips likely have a hard-coded limit in their firmware that simply cannot process a password longer than 12 characters. If SEC allowed a 16-character password, it would instantly lose the ability to talk to half the data center.
So it's the lowest common denominator problem? You have to lower the ceiling on the new software so it doesn't break the old hardware?
Precisely. It perfectly illustrates the compromises required in the real world. You are forced to lock the front door with a slightly shorter key, which is exactly why you have to compensate by putting that massive, unyielding 15-minute time lock on the porch.
That makes perfect sense. Okay, so I'm the admin. I've successfully navigated the TLS certificates. I've typed in my 12-character password without triggering the time lock, and I'm staring at the dashboard.
Welcome to the cockpit.
Right. What do I actually do all day? The interface categorizes the entire workflow of the data center into 3 very distinct buckets: tasks, activities, and events.
It's vital to distinguish between these 3 because they represent the fundamental flow of information. They dictate who is talking to whom.
Okay, let's start with tasks.
Tasks are proactive. These are the commands the human administrator or an automated script issues to the system.
Like actionable operations. The interface shows examples like delete node or deploy OS.
Right.
You get a ledger showing the start time, end time, state, and result. And looking at the state column, you realize this isn't just a simple list of successes.
Not at all.
The reality of software hitting physical hardware is messy. The text shows a task failing with the error, quote, exception, javax.trans, unquote. Why is a Java transaction failing when I'm just trying to deploy an operating system?
Because enterprise software is built in layers. SuperCloud Composer is likely built on a Java backend. When you click Deploy OS, that Java code has to reach out over the network, wake up a physical server, tell its storage array to mount a new drive, and begin copying data.
That's a lot of steps.
It is. 100 different physical things could interrupt that. A network switch might be momentarily congested. A hard drive might have a bad sector. When the physical world fails, it bubbles up through the software layers and presents itself as a Java transaction exception on your dashboard.
So tasks are what I tell the data center to do. What are events?
Events are the exact opposite.
Yeah.
Events are reactive. This is the hardware screaming up at the administrator.
It's screaming up.
Yeah. These are raw notifications originating from the BIOS or the BMC on the motherboard itself.
Things like the system was powered on or set boot order instance is the bare metal sending up flares to say, hey, my physical state just changed.
Exactly.
And then the third bucket is activities.
Activities act as the broad, overarching audit trail. It logs the macro-level system actions, allocate and assemble, create composed node, delete account. It is a historical record of who did what and when, which is critical for compliance and security auditing.
The UI handles all this incoming data with notification badges in the top right corner, sort of like an email inbox. A gavel icon for tasks, a bell for activities, a pulse line for events.
Yeah, very standard iconography.
But there is an incredibly specific UI detail regarding timestamps that I found absolutely fascinating.
Oh, the 48-hour shift.
Yes, it states that if an event or task is newer than 48 hours, it displays the time relatively, like 2 hours ago or 5 minutes ago. But the second it crosses that 48-hour threshold, the UI shifts and displays a hard calendar date, like 04182026.
To great detail.
Why design it that way? Why not just show the exact date and time all the time?
That is a brilliant piece of UI design rooted entirely in human cognitive psychology. When a human administrator is performing operational triage, they're thinking in relative time. Their mental model is, did this server fail on my shift or the guy before me?
Right.
If you see a hard date like April 18th, 14.03, your brain has to perform a series of calculations. Okay, today is the 18th. It's currently 16.00. So that was roughly 2 hours ago.
You were wasting mental energy on math instead of actually fixing the problem.
Exactly. 2 hours ago is instantly processable. It carries urgency. But once an event passes that 48-hour window, it completely loses its operational urgency. It shifts from being an active fire to historical data.
Hi.
At that point, saying 73 hours ago is useless. You want a hard calendar date so you can easily cross-reference it with a changelog or a maintenance schedule. The UI adapts to the specific cognitive task the human is performing at that exact moment.
And cognitive load is a huge factor here. When you look at the main dashboard view, it is just a staggering wall of data. There are widgets for rack server POD health flashing critical alerts, system allocated rings showing resource usage.
It's a lot to take in.
But the one that really stopped me in my tracks was the liquid cooling health check.
Oh, yeah.
It's tracking CDU leak sensor traps and server leak sensor traps. You are managing thousands of highly sensitive electronic components, and right next to the Java exceptions, you have an alarm specifically designed to tell you if water is physically leaking onto the motherboards.
This raises a really important question about how a single human being can possibly process this without suffering a nervous breakdown.
Honestly, yeah.
Think about it. You have a dashboard flashing red for a failed server deployment, yellow for a network latency issue, and critical red for a potential liquid coolant leak, all simultaneously. It's like being an air traffic controller, but instead of planes, you are managing millions of moving physical and logical parts.
Without a perfectly structured way to navigate and filter this information, the administrator would suffer from severe alarm fatigue. They would just stop seeing the alerts entirely.
Exactly. And that's where the data browser comes in.
Right. Okay, so I'm that admin. I've got 40 tasks failing, a Java exception, and 3 liquid cooling leaks going off. How do I not have a panic attack? How do I actually find the leaking pipe in a windowless warehouse the size of 3 football fields?
The data browser is essentially the Rosetta Stone of the entire platform. It is the tool that translates a blinking red alert on a screen back into a physical box in the real world. And the hierarchy it uses is incredibly strict.
It starts at the macro level with a POD. The text defines a POD as a physical collection of multiple racks. That sounds innocuous, but what are we actually talking about in physical terms?
A POD is massive. Depending on the architecture, a POD could be 20 or 30 large metal racks bolted together, sharing a common power spine and a common network switch. It's a massive, self-contained ecosystem of computing power.
And inside a POD, you have a group, which is a logical subsection.
Mm-hmm.
Then you drill down to the rack itself, and inside the rack is a drawer.
Yes.
I love that they use the word drawer. It defines it as, quote, a kind of chassis, which can contain one or multiple systems.
It's a very evocative term because it accurately describes the physical reality. If a technician is on the floor, they literally grab 2 handles and pull out a heavy, sliding metal drawer from the rack. Inside that drawer is the delicate silicon, the compute nodes, or the storage drives.
And finally, inside the drawer, you reach the appliance, the individual node. The UI gives you 2 ways to look at this map. The tree view, which is a massive hierarchical list expanding downwards, and the module navigation view, which is more graphical.
Right.
And the design guidelines for this UI are incredibly specific. For example, in the tree view, an enabled icon has a 15% opacity white background. But when your mouse hovers over it, it shifts to 100% opacity with a solid white border.
Yeah.
It sounds like such a minor aesthetic choice, but why document it so heavily?
Because when you are staring at a screen containing thousands of nearly identical tiny icons representing servers, visual clarity is the only thing preventing catastrophic mistakes.
Oh, that makes sense.
If your eyes are bleeding from an 8-hour shift, that subtle shift from 15% to 100% opacity is the only tactile feedback you have to guarantee you are about to reboot server 42 and not the mission-critical database on server 43.
But the most terrifying visual cues in the data browser are the warning icons. There's an X for exceptions, a regular question mark for authentication problems, and a red question mark for what they call a stale node.
Ah, the stale node.
The text defines a stale node as, the node is no longer accessible from SEC. Please check it and see if any connectivity issue. If the node is removed physically by expectation, please delete it.
A stale node is pure terror for a system administrator. An exception means something broke, but the system still knows it exists. A stale node means a piece of hardware has simply ceased to exist from the software's perspective. It has gone completely dark. It's just a void.
It's like Houston losing telemetry from the space shuttle. You just have no idea what's happening.
Yeah.
Did a $50,000 server just melt? Did an intern spill a cup of coffee on a power strip? Or did someone just trip over a fiber optic cable in the dark?
Exactly. You don't know until you go look. And the regular question mark icon, the authentication problem, is equally revealing about the physical reality of data centers. The text notes this happens if credentials changed in unusual ways.
So the software is saying, hey, I had the password to this drawer yesterday, and now I don't. How does that happen if the software didn't do it?
It means someone bypassed the software entirely.
Oh.
In a real data center, if a server completely locks up, a technician will physically walk down the refrigerated aisle, roll a literal metal cart with a monitor and a keyboard on it called a crash cart, plug it directly into the front of the server blade, and manually reset the root passwords at the hardware level.
So the SEC dashboard is sitting hundreds of miles away in a control room, suddenly realizing someone changed the locks on the physical box while it wasn't looking.
Precisely.
So what does this all mean for the UI design? Think about the hyper-efficiency required to navigate this. You are sitting in a control room. You click POD. You scroll down. You click Rack 14. You expand it. You scroll down. You click Drawer 3. You are virtually drilling through steel and silicon.
It's a deep dive every time.
Yeah. And the manual notes this very specific quirk about the view toggle icons. It says the tree view and navigation view icons, quote, are grouped together. They appear like they're stick together to the right side of the data browser, unquote. If you drag the scroll bar, those icons float and follow you down the page.
It's a beautiful example of pixel optimization. When you have drilled down past thousands of nodes to find one specific blade in Rack 14, you do not want to scroll all the way back to the top of the web page just to toggle how the data is displayed.
No, that would be so annoying.
Those icons are glued to the edge of the viewport, so they're always exactly 1 millimeter away from your mouse pointer. In a system where seconds count during an outage, you optimize every single pixel of mouse movement.
All right, so we've drilled all the way down the tree view. We've bypassed the PODs, the racks, the drawers. We're finally hitting the bare metal. And the glossary of this manual provides a massive treasure trove of vocabulary that decodes what this cutting-edge hardware actually is. Let's start with my absolute favorite term in the entire document, JBOF.
Just a bunch of flash.
Just a bunch of flash. It sounds like an insult.
Right.
Like, oh, don't worry about that box over there. It's just a bunch of flash.
Right.
But the reality is that a JBOF is a marvel of engineering. The glossary defines it as a chassis that houses a pool of flash-based storage.
To appreciate why a JBOF is revolutionary, we have to go back to the legacy server model we discussed earlier. A traditional server had a motherboard with a CPU, and physically connected to that motherboard were 3 or 4 hard drives. The storage was permanently married to the brain.
Right.
If you wanted to upgrade the storage, you had to power down the brain, open the case, and physically swap the drives.
Which means downtime, which means lost money.
Yes. A JBOF completely divorces the storage from the brain. It is literally just a heavy metal drawer taking up maybe 2 units of rack space, packed front to back with unimaginably fast solid-state memory drives.
Wow.
There is no major computer in there. It's just a raw, dense pool of data capacity sitting independently in the rack.
And because of the composable architecture we talked about earlier, SEZ can mathematically slice up that box of flash and serve chunks of it over the network to any compute node that asks for it.
Exactly.
But here's the critical problem. If my brain is in Rack A and my hard drive is in a JBOF in Rack B, doesn't the data take longer to travel over the network cables between them? Doesn't that physical distance create a massive bottleneck that defeats the purpose of fast flash memory?
That is the multi-billion-dollar physics problem of the modern data center. And the manual explains exactly how they solve it using 2 technologies, NVMe and NVMeOF.
Let's unpack those. NVMe stands for Non-Volatile Memory Express.
Right. Historically, hard drives connected to motherboards using cables and protocols like SATA. SATA was designed for spinning magnetic disks, and it had a hard speed limit about 6 gigabits per second.
Okay.
But modern solid-state flash memory is so incredibly fast that the SATA cable itself became a traffic jam. The memory chips were literally waiting around idle for the cable to slowly carry the data away.
And the manual explains that NVMe bypasses those old cables entirely. It connects the storage devices directly into the PCI Express lanes, the PCIe interfaces, it states. Typically, 4 PCIe lanes are allocated per disk. Performance for one PCIe 3.0 lane is 1 Gbps.
PCIe lanes are essentially the brainstem of the computer. By plugging the storage directly into the PCIe bus, the CPU can talk to the storage at near instantaneous speeds.
Inaudible.
But that still requires the drive to be physically close to the CPU. To solve your question about Rack A talking to Rack B, we use NVMe OS NVMe over Fabrics.
And Fabrics is just a fancy word for a highly specialized, insanely fast local network, right?
Exactly. But it uses specialized protocols like RDMA Remote Direct Memory Access.
Okay, what does that do?
RDMA allows the CPU in Rack A to reach across the network fabric and read data directly out of the flash memory in the JBOF in Rack B, completely bypassing the operating system and the traditional network stack of both machines.
Wait, really? So the software doesn't have to politely ask the network card to ask the other network card to retrieve a file. The brain just reaches across the wire and grabs it directly from the memory chip.
It happens with such low latency, literally measured in microseconds, that the CPU in Rack A literally cannot tell that the hard drive is 50 feet away. It operates as if the drive is physically bolted onto its own motherboard. It is disaggregation without any performance penalty.
And because you have these massive pools of lightning-fast shared storage, it completely fundamentally changes how administrators deploy software. The manual goes deep into LVM Logical Volume Manager, which enables things like RAID, cloning, and snapshots, and ties this all together into a concept called fast deploy using a golden image. Now, a golden image is defined here as, quote, a bootable OS image that can be used for fast deploy of an OS.
Right.
Let's ground this in reality for a second. Think about what happens when a relatively small website suddenly goes viral. Millions of people hit the site at the same time. In the past, if an admin needed to spin up new servers to handle that massive traffic spike, they had to virtually mount a Windows or Linux installation disk.
Yeah, the old way.
They had to click install, watch a progress bar, slowly extract files, configure registries, install drivers. It could take an hour to boot up a new server. By the time it was ready, the website had already crashed and the viral moment was over.
That is the nightmare scenario. But with a golden image, combined with LVM snapshots running over an NVMe fabric, the paradigm is completely inverted.
How so?
The administrator takes their time to install a perfect, pristine, highly optimized version of an operating system. That is the golden image. It sits in the JBOF storage pool.
And when that traffic spike hits,
the SEC software detects the load. It dynamically grabs loose compute power from the hardware pool. It commands the LVM to take an instantaneous logical snapshot of the golden image. Because of the sheer speed of NVMe, it maps that snapshot to the new compute nodes almost instantly. You don't install an operating system, you clone a running state.
So within 10 seconds, 50 brand new, fully booted, perfectly configured virtual servers spring into existence to handle the web traffic.
Exactly.
And when the traffic dies down the next day, SEC deletes the snapshots and returns the compute power to the pool. It fundamentally changes the definition of what a computer is. It's no longer a physical thing. It's just a temporary, fleeting manifestation of logical rules applied to a massive hardware pool.
It is brilliant. But we cannot ignore the physical toll that this blistering speed takes on the real world.
Right, the heat.
You cannot push that much data and that much electricity through silicon without generating catastrophic consequences. Which brings us to the final, perhaps most crucial elements in the glossary, LCC and PDU.
LCC stands for Liquid Cooling Console, and PDU is Power Distribution Unit. We mentioned those physical leak sensors earlier on the dashboard. But why is liquid cooling so mandatory now? I mean, my laptop has a fan. My gaming PC has a bigger fan. Why can't we just use giant fans?
It comes down to the thermodynamics of modern artificial intelligence and composable compute nodes. The power density, the amount of electricity being forced into a tiny square of silicon has skyrocketed. We are moving past the physical limits of air cooling. Air simply cannot absorb and carry away heat fast enough. If you put a massive fan on a modern AI supercluster chip, the chip would still melt itself into slag in seconds.
So they have to use a liquid.
They had to pump chilled, highly specialized liquids, sometimes water, sometimes engineered coolants directly through microchannels in cold plates sitting flush against the CPUs and GPUs.
Okay.
The liquid cooling console is the software that manages the pumps, the pressure, the flow rate, and the ambient temperature of that liquid.
Think about the risk profile of that. You have tens of millions of dollars of incredibly sensitive electronics, and you are deliberately weaving pressurized pipes filled with liquid right across the top of them.
That sounds crazy, right?
It does. If the LCC software crashes or a pump fails, the coolant stops flowing and the hardware literally cooks itself.
Managing the thermodynamics is now just as critical a software task as managing the network traffic. It paints a wild, incredibly vivid picture of the modern server rack.
It really does. It's not just a bunch of beige PCs stacked on a metal shelf anymore.
Yeah.
Imagine standing inside the POD. You have a massive reinforced steel frame. Inside there's a heavy metal drawer consisting of nothing but pure glowing CPU power. Below it, a completely separate drawer of pure JBOF flash storage.
Yeah.
Thick, insulated liquid cooling pipes are weaving between them like physical arteries, pulsing with chilled water. High-speed fiber optic cables are carrying data at the speed of light using RDMA. And sitting above it all, acting as the invisible brain, the conductor of the orchestra, is the SuperCloud Composer software, silently linking them together, monitoring the water pressure, shifting resources millisecond by millisecond.
It is a phenomenal, almost terrifying engineering achievement. When you really analyze this manual, it ceases to be a dry guide on how to click menu buttons. It becomes a window into the absolute bleeding edge of human technological infrastructure.
Let's take a breath and recap the journey we just took through this document. We started with the abstract philosophy of composable infrastructure, realizing that modern data centers are just massive pools of disaggregated resources waiting to be assembled like Lego bricks.
Right.
We walked through the stringent security gates, learning why PM headers and mathematically calculated time locks are the only things keeping automated botnets out. We sat in the operator's cockpit, parsing the difference between proactive tasks failing with Java exceptions and reactive hardware events screaming about motherboards.
It's a lot of data.
It is. We navigated the digital topography using the data browser's hyper-efficient UI to hunt down terrifying stale nodes in the dark. And finally, we drilled down to the bare metal, exploring how JBOFs, NVMe network fabrics, and pressurized liquid cooling pipes physically make the cloud possible.
We really covered a lot of ground today.
I want you, the listener, to remember this deep dive the next time you tap an app on your phone to load a video, and it plays instantly. That frictionless, weightless experience only exists because, right at this very moment, in a freezing cold, deafeningly loud room, software like SuperCloud Composer is frantically orchestrating a high-speed, mind-bogglingly complex mechanical ballet of hardware behind the scenes.
And if you look forward, I'll leave you with one final thought to mull over. We've seen today how platforms like SCC have become incredibly proficient at abstracting physical, heavy hardware into pure, logical software objects. We also know that artificial intelligence is advancing rapidly, capable of analyzing logs and predicting failures faster than any human.
That's true.
If the software can compose the hardware perfectly via APIs, and if AI can eventually triage the tasks, analyze the events, and automatically clone the golden images to fix outages, are we approaching a future where human engineers never actually need to understand the physical hardware at all?
Wow.
Will the modern data center eventually evolve into a locked, dark, windowless box that completely fixes, cooled, and recomposes itself, rendering the human IT administrator entirely obsolete?
A locked, freezing box where the Lego spaceship just builds itself in the dark. It's a fascinating and honestly slightly chilling thought. Thank you for joining us as we unpack the heavy physical reality behind the cloud. Until next time.